Welcome to this product demonstration video. My name is John Meister, Application Engineer with Keysight Technologies, and I just wanted to spend a little bit of time today to show you a configuration using our new UXG series signal generators. The UXG signal generator is composed of an analog portfolio family and a vector family. So the N5193 is the analog UXG source, which you can see here on the bottom of the stack. This is a very agile, highly dynamic source that can stream PDWs as well as a variety of other signals, and we can modify amplitude, frequency, phase, or timing of a pulsed or CW signal very dynamically. And then what we've just recently introduced is the N5194A vector adapter, and that allows the addition of IQ modulation on top of the dynamic PDW signal generation capability. The family also is natively capable of doing coherent operations, so you can see here the configuration that I've set up is an analog UXG on the bottom, which operates as the local oscillator and frequency source. And then I've got two vector adapters, N5194 vector adapters, that I'll be playing a variety of different signals out of. And I wanted to just show a couple of examples of doing this kind of signal generation. You can see on the interconnect diagram that there are a variety of connections that need to take place. One of them is a local oscillator being split in between both vector adapters, which will operate as up converters. The 6 GHz reference clock is distributed across all sources, and then there's a variety of control and trigger lines that are connected up as shown in the diagram. So the first signal we're going to take a look at is called an amplitude walk. So basically I'm generating a series of pulses that all have the same pulse width and PRI, and effectively I'm walking the amplitude down in 5 dB increments. So we basically can just simply input a spreadsheet into the source, into the vector adapter source, and it defines the frequency, phase, amplitude, timing parameters, IQ content, and so forth, and modulation on the pulse and things like that. So in this case I've basically just done a simple repetitive set of pulses that drop 5 dB per increment. And the display that you're seeing is our pulse analysis utility that is an option on our signal analyzers. So if I, for instance, just to show you, I can enable a measurement here, select a spectrum analyzer mode, a normal spectrum analyzer mode, and say OK. And so you can see here we're running our X-series signal analyzer. Our signal itself is a range of pulses that are available here that you can view in the frequency domain. And so we can actually go in and do normal spectrum analysis adjustments with this. I could reduce the bandwidth to get our classic sin x over x response that you would expect to see. But the analyzer itself has a pulse option mode, which I've invoked here. And what we can do with this mode is basically collect PDW parameters, things like modulation on the pulse, amplitude, frequency, phase, modulation, Barker coding, chirp decodes, and things like that. But there's also a scatogram plot, which is sort of handy to show some of these capabilities here. So with the scatogram I can pick any two parameters and plot them against each other. So in this case we're using pulse number on the x-axis, amplitude on the y-axis. And what I'll do is, just for stability's sake, I'm going to go ahead and do a single sweep on this so we're stable. We have, as you can see, a variety of pulses that it's acquiring, and we can actually look at from one pulse to the next. We see our 5 dB per division y-axis, and we're walking the amplitude down and then restarting and walking the amplitude down again and repeating the pattern. In actuality, the levels I've got go below 90 dBm, but our current system noise floor is set at around minus 70 or so. So we're not, and our detection criteria is not all the way down to the noise floor, but you can see how it's accurately repeating this 5 dB increment. So here I've modified the signal coming out of the source to a constant amplitude set of pulses. If you can refer to the table here, the pulse width is 1 microsecond on all the pulses. The pulse period is 10 microseconds, and there's various other parameters. There's no modulation on the pulse as we're detecting, and these pulses are about minus 11 dBm across the way. So what I want to do is switch over to the scatter plot again. So if I go to my basic graphs, it's my scatter plot. And what I want to do is change the values that I'm plotting. So I want, because I can plot any parameter against any other parameter, I'm going to select on the x-axis pulse number, and on the y-axis I want to do the phase, the mean phase. Okay, so after setting everything up and doing the acquisition, showing our phase walk, you can see on the bottom trace we've got pulse number, in other words the order of the pulses that were coming in, and then the y-axis is phase, and I'm at about a 30-degree per division adjustment. So what I've done is put two markers on the first point here on this lower left indicator point, and what I can do is step the marker from pulse to pulse effectively to record the phase values, and you'll be able to denote the delta over here on the marker readout section. So if I jump to the next pulse, first if I select the marker, go to the next pulse, you can see that from the increment of the next pulse over, I'm transitioning about 16 degrees. I'm actually doing about a 15-degree step per pulse. So you can see every pulse increments another additive 15 degrees into the rotation. So I can continue to step through, and when the cycle resumes, it increments by 15 degrees as a starting point. So you can see how it continually rotates up through the next set of pulses, and then this pulse will be 30 degrees at the start, and so forth. So you can see how we can readily do all kinds of phase and amplitude control based on what we've shown. So this concludes the demonstration. If you have any questions, please contact Keysight Technologies. Thank you so much.